Good morning, everybody. I thought maybe today we could review for the exam, which is on Tuesday. And so I just have some sample problems here for us to work through. Okay, and how about let's try some product prediction problems first of all. So I hope you had time to review a lot of these reactions. So I'm thinking of just writing the starting materials and then waiting a little while, and you can self-test to see whether you're coming up with the correct answer. Okay, so draw the structure of the product. So what reaction is this? Anybody out there want to give it a shot? Maybe you can unmute yourself. What reaction is this? Baeyer-Villiger. So it's the reaction of a ketone with a peroxy acid, and the most popular peroxy acid is MCPBA. And what is going to happen here is the insertion of oxygen between the carbonyl carbon and a neighboring carbon. But when there is a choice, that neighboring carbon should be the more substituted neighboring carbon. So this carbon over here, this is quaternary. It's bonded to 4 different carbons. This carbon over here is secondary, so the oxygen is going to insert itself between the quaternary carbon and the carbonyl carbon. So the product here is going to be written in a hideously ugly way, and unrealistic way, but just trying to emphasize how oxygen inserts itself between the carbonyl carbon and the more substituted neighboring carbon. And also important to note, it's with retention of stereochemistry at the more substituted carbon. So that's a wedge in the product, it's a wedge. So how do we do? Okay, let's try another one. Okay, so draw the structure of the product here. So what reaction is this? So that is Tollens oxidation, in which an aldehyde is oxidized to a carboxylate by the action of silver ion under basic conditions. So that's what happens in the first step, the oxidation of the aldehyde to a carboxylate. And then this step 2 is in there because we don't usually want the carboxylate. We usually want the carboxylic acid. So just do this in a stepwise way. First step oxidizes the aldehyde to a carboxylate. All right, so that's what we would get at the end of step one. It's an oxidation. And remember we said that one of the hallmarks of oxidation is something gets more bonds to oxygen. So this carbon atom here, this aldehyde carbon, starts life with 2 bonds to oxygen. Now it has 3. So that's the oxidation. But step one has this hydroxide ion in there. So that's basic conditions. You get this carboxylate. Remember we said every time you see an oxygen atom with a negative charge, that's going to be a base. Well, that makes sense because step one is basic conditions. It's only after acid workup that the carboxylic acid is produced. So at the end of step one, we have that carboxylate, and at the end of step two, with that aqueous workup, that's what gives us the carboxylic acid. So I'm mentioning this thing about the acid workup because it's important that we realize that we need it. Okay, a few more product prediction problems, just reviewing for exam number 2. Okay, so let's draw the structure of the product here. So let me clean this up a little bit to make it look pretty. So this is a Grignard reaction. So aldehydes, ketones, lots of stuff reacts with a Grignard reagent. But remember that nucleophiles attack the carbonyl carbon along the Bürgi-Dunitz trajectory, meaning from above and below the plane of the carbonyl, and making a 109-degree angle with the carbonyl group. But it's also important to remember that the nucleophile, if there is a choice, enters along the path of least resistance. It attacks the face of the carbonyl carbon that is less sterically hindered. So the nucleophile is going to attack this carbonyl, but is it going to attack from the top or from the bottom? So think about that. Yeah, it's going to attack from the bottom, because if it attacked from the top, it would have to manage its way past the stick-up methyl group, and that's much more sterically hindered road in than attack from the bottom. And so the product here, after acid workup, that what used to be the carbonyl carbon now has a methyl group on it. And we're drawing a chair conformation. Remember, chairs have axial and equatorial bonds. So there I've written the axial and the equatorial bonds on what used to be the carbonyl carbon. And now tell me, that methyl group, is he axial or is he equatorial? Well, he's equatorial because the nucleophile came in from the bottom. And the carbonyl oxygen was converted to an alcoholic oxygen, so that would be the product of that reaction. So how are we doing out there? All right, a few more product prediction. you're just going through some of these important reactions. Draw the structure of the product here. So what is the product here going to be? This is the recipe for the enamine. It's an aldehyde or a ketone plus a secondary amine. What's a secondary amine? Secondary amine is NH. So this is what should call to mind that it's a secondary amine, NH. A primary amine is NH2. So this is a secondary amine. So the product here is going to be an enamine in which that nitrogen atom attacks what used to be the carbonyl carbon, and it sets up a double bond between what used to be the carbonyl carbon and the neighboring carbon. Now, there's all kinds of, so what I've written here is the C stereoisomer. I drew that just for looks. You probably get the E stereoisomer as the major product. So maybe something like that would be a little bit closer to the truth. This morpholete group is pretty big. It's going to, so this trans double bond is probably going to be favored. The other product of this reaction is going to be water, but that's the inorganic product we don't really care too much about. Okay, so let's try some more. How we doing? Good, I hope. First step, sodium cyanide and HCN. Second step, excess hydrogen and a nickel catalyst. So let's draw the structure of the product here. Okay, step one, that's hydrocyanation, the reaction of an aldehyde or ketone with sodium cyanide in the presence of hydrogen cyanide. So at the end of step one, what we get is a cyanohydrin, where the cyanide ion attacks what used to be the carbonyl carbon, so this is a cyanohydrin. And I wrote the carbon-nitrogen triple bond there explicitly because that will help to understand what happens in step two, which is the total reduction of the carbon-nitrogen triple bond to a carbon-nitrogen single bond with the addition of hydrogen. So the product here is this primary amine. All right, so this first step, that's something that's a reaction of aldehydes or ketones. But the second step here, this is what you can do with the cyanohydrin in case you have to write out a synthesis problem where the product would be a primary amine. This would be one way of accomplishing that. Okay, it's more. Oh, this one looks like it's going to be a toughie. Okay, let's draw the structure of the product here. Okay, so this problem belongs to the hemiacetal acetal manifold of reactions. So let's just, because this is pretty important chemistry, let's just review what's going on there. Hemiacetal, that's an sp3 hybridized carbon. sp3 hybridized carbon bonded to two oxygens, one of which is an OH oxygen and the other one is not. So that's the hemiacetal. The hemiacetal is the recipe for forming the hemiacetal is an aldehyde or a ketone plus one equivalent of alcohol. So this thing is in equilibrium with that hemiacetal carbon used to be a carbonyl carbon, and the oxygen atom that is not part of the OH group, that used to be an alcoholic oxygen. And we need acidic conditions. But here I was careful to draw the equilibrium arrows showing that the reaction is reversible. So actually, it's an aldehyde or ketone plus an alcohol plus acid, and water is also produced. Okay, then we have the acetal. And what's an acetal? The acetal is an sp3 hybridized carbon, once again bonded to two oxygens, but neither of those oxygens are OH oxygens. So I could write it, that's OR, and maybe this is OR prime, but these could be the same or they could be different. So that's an acetal. And the recipe for the acetal is a carbonyl compound, an aldehyde or a ketone, and these acetal oxygens were alcoholic oxygens. So we need one equivalent of ROH, and then we need a second equivalent of R prime OH. Okay, so the difference between the hemiacetal and the acetal for conditions of formation is that for the acetal, you have two equivalents or an excess of alcohol, whereas for a hemiacetal, you only have one equivalent of alcohol. Okay, so look at this guy here. Is he a hemiacetal or is he an acetal? He's an acetal. There's an sp3 hybridized carbon bonded to two oxygens, neither of which is an OH oxygen. So this guy here, he's an acetal. And when we add acid and water to an acetal, that reverses the equilibrium. The acetal oxygens fall off as OH oxygens. and the acetal carbon reverts to a carbonyl carbon. Okay, so the product here is going to be drawn in a very ugly and unrealistic way. See, those are the acetal oxygens that fell off the acetal carbon as OH oxygens. But the rest of the molecule, now here we get the acetal carbon. And when treated with aqueous acid, the acetal carbon reverts to a carbonyl carbon. So that's a hideously ugly drawing of the product, but I think that makes the point. Okay, a few more here. Okay, so this one is a Lonnie. Step 1. Step 2. Step 3. Okay, so let's draw the structure of the product here. What happens when everything is said and done in this reaction? So do you recognize what the reaction is? Yeah, this is that Horner-Wadsworth-Emmons modification of the Wittig reaction. Step 1 is the Arbuzov reaction. So step 1, phosphorus is a nucleophile. Phosphorus attacks the carbon atom that bears the bromine in an SN2 reaction. And then the bromine whips around and does another SN2 reaction on the adduct. So at the end of step 1, what we would have is we have that phosphone. I think that's what it's called. We have this phosphone. That's what we get at the end of step 1. So that's the Arbuzov reaction. Okay, so now step 2 is the deprotonation of the carbon atom that is sandwiched in, or rather the carbon atom that is next to the phosphorus. And that makes the ylide. Okay, so that's what we get at the end of step 2. And now step 3 is the formation of that carbon-carbon double bond. Because remember, this is a variation of the Wittig reaction. The Wittig reaction is a way of making a carbon-carbon double bond, where now I'm going to hook up the carbon atom that has that negative charge on it. and I'm going to hook up the carbonyl carbon of the aldehyde or the ketone, and that's going to form a new double bond. And but now the issue to remember here is that when this negative charge on this ylid-like structure can be delocalized by resonance, you're going to get the E-alkene. You're going to get the trans-alkene. So I'm hooking up the star and the dot, but I'm going to hook them up E-style. There's my star. There's my dot. I hook them up. But now I have to remember that this gives the E-alkene. So I'm putting my fishtail over here. Okay. All right, how about one more product prediction problem, and then we can transition into some mechanism and synthesis. Okay, so draw the structure of the product there. Okay, so this is the recipe for an imine. It's an aldehyde or a ketone and a primary amine. So this is a primary amine. What's primary amine? NH2. And this is a tertiary amine. So so there should be no question about whether it's an enamine or an imine. We did an enamine earlier. This is going to be the imine. And an imine, in the reaction of the formation of the imine, you replace the carbon-oxygen double bond of the aldehyde or ketone with a carbon-nitrogen double bond of the imine. But nitrogen forms 3 bonds when it's neutral. So this and this dimethyl amino group just goes along for the ride. And so that would be the product. And once again, with this imine, form this stereogenic double bond. This can come out in both E and Z flavors, but as usual, the trans double bond, the trans carbon nitrogen double bond is more favored because it's just less sterically hindered product. Okay. So that was some product prediction of some reactions. Since we only have an hour, I can't possibly go through everything. So let's try some mechanism. Okay, so let's write out a mechanism for this reaction. So what reaction are we talking about here? Look at this product. It's an acetate. It has a carbon atom, sp3 hybridized, bonded to two oxygens, neither of which is an OH oxygen. So that's the acetal, and let's write out mechanism. Okay, so one strategy for writing out mechanisms is we look at which atom in the reactant is which atom in the product, and we know that usually only 5 things ever happen in a mechanism problem, and that would be protonation, deprotonation, nucleophile attacks electrophile, departure of a leaving group, and a carbocation rearrangement. So that before we write any steps on our piece of paper, maybe we can look at the reactant, look at the product, and try to figure out what exactly happened to each atom. This oxygen atom here, I'm going to put him in boldface. He's this one. And what did he do? Well, he lost a proton, so we're going to have his deprotonation as one of the steps. Another thing that this oxygen did was that he is now bonded to this carbon here that has this phenyl ring on it. And so this carbon, I'm putting a dot on him. He's here, he's there. And so this new boldface oxygen dot carbon bond was created. So how did that happen? This guy had to be a nucleophile. Okay, so now if we look at this oxygen down here, what did he do? Well, he's also bonded to the carbon with the dot. He also lost a proton. So in our mechanism, this guy also is going to undergo a deprotonation, and he also has to function as a nucleophile. Okay, and so now what about this oxygen? Well, he's gone. He came out as a molecule of water. He used to be bonded to the dot, but he is no longer bonded to the dot. So this oxygen atom here, he gained 2 protons, and he also had to be a leaving group, because this is how we break bonds, how we would break a bond between a carbon and an oxygen. That's not the only way, it's just the most common way. Okay, so we set goals. I'm predicting a 1, 2, 3, 4, 5, 6, 7 step mechanism. What's the first step? One of the motifs that we see repeatedly is that when you have a carbonyl compound sitting around an acid, what are the first 2 things that happen nearly all the time? Protonate the carbonyl oxygen and then attack the carbonyl carbon with a nucleophile. Okay, so to get things going with our mechanism problem here, that's what I would do first. Protonate the carbonyl oxygen and then attack the carbonyl carbon with a nucleophile. And so a boldface oxygen is a nucleophile, and this other oxygen is also a nucleophile. Which one attacks first? I guess on an exam or something like that, it really wouldn't matter. But because this oxygen is enjoying resonance with this benzene ring, whereas this oxygen is not, whereas this oxygen, his electron pair is tied up with resonance with the benzene, probably this one is going to be more nucleophilic, because his electron pairs aren't enjoying resonance with benzene. They're more available for bond formation. So this guy, I'm going to let him attack first. But on the test, I don't think it would really matter which oxygen you attack with first. Okay, so that would be the intermediate that we would get as the result of attack by that oxygen atom on what used to be the carbonyl carbon. Okay, so how am I doing on my checklist here? Protonate the carbonyl oxygen one time, yep. Attack the this oxygen here, did he function as a nucleophile, yep. Okay, and so now there's a lot of fiddling and diddling with protons, because now what has to happen is that this oxygen has to somehow be expelled as a molecule of water. So I'm just going to write all of that fiddling and diddling with protons using this symbol plus minus H plus, meaning take a proton away from somewhere in the molecule and bring the proton back somewhere else on the molecule. So what I'm going to do is take that proton away from that positively charged oxygen. Oxygen is very electronegative. It doesn't like to have that positive charge. And I'm going to bring that proton back over here on this oxygen, which is about to function as a leaving group. So remember, whenever we see a positively charged oxygen, it's usually going to do one of two things. One of them is undergo deprotonation. The other thing is going to be function as a leaving group. So I deprotonated this guy. Check. I protonated this guy. I protonated this guy. Check. Okay, and so now this can function as a leaving group. So that loses water. Wrong. And we get this tremendously stabilized carbocation. So this carbocation is stabilized by resonance with this oxygen. It's also resonance stabilized by that phenyl ring. Okay, so this oxygen functioned as a leaving group. Check. Okay, and so now what's left is that this oxygen, let's see, check, 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 check. Now this oxygen here does all of his business. It's going to be a nucleophile. It's going to undergo deprotonation. So that's going to bring the mechanism to the close. Okay, next step. That's the electrophile. He's electron poor. There's the nucleophile. He's electron rich. So nucleophile attacks electrophile. That oxygen functioned as a nucleophile. So this is looking pretty good. This is looking very much like our product already. And now the last step is going to be deprotonation of that positively charged oxygen, and that brings our mechanism to a close. All right, so there's the mechanism for formation of an acetate.
Professor Rubio, I have a question.
Yes, go ahead.
On the exam, are we allowed to write the plus or minus H plus like you did as one?
Yeah, that would be fine.
Okay, thank you.
All right, so just some comments about writing this mechanism. It's acidic conditions. So when you write a mechanism under acidic conditions, that means you can't have any strong bases. That means for this guy here, no O minus anywhere. O minus is a strong base. So what is one of the most common mistakes that people would make is that this step here, where this oxygen functions as a nucleophile and attacks this carbonyl carbon, or this step here, where this oxygen functions as a nucleophile and attacks this carbocation. Most common mistake I've seen a bazillion times is people whack this proton off and now you have O minus. But you're under acidic conditions, no C minus, H minus, O minus, or N minus anywhere, right? And if this were an imine mechanism, then we wouldn't have an N minus anywhere. So acidic conditions can't have any strong bases, and we've gone through how we can identify what is and what is not a strong base. Okay, how about let's try one more mechanism and then finish up with a synthesis. Okay, so let's try to cook up a mechanism for this reaction. And again, you know, if you have gobs and gobs of time until you develop instincts, look at the reactant, look at the product, try to figure out which atom in the reactant is which atom in the product, and what exactly happened. Only 5 things can happen: protonation, deprotonation, nucleophile attacks electrophile, and a carbocation rearrangement. This nitrogen protonated 2 times. This carbon-nitrogen bond has been broken, so this nitrogen atom had to be a leaving group. Okay, this oxygen here of water, he's clearly the oxygen atom that is the carbonyl compound, so what all did he do? 2 deprotonations, lose a proton 2 times, and what else did he do? He is now bonded to what used to be this iminium ion carbon. I'm putting a dot on him. So he had to be a nucleophile. Okay, is that pretty much it? Yeah, that's pretty much it. So I'm predicting a 1, 2, 3, 4, 5, maybe 6-step mechanism. What would be the first step? Would I protonate him? No, a proton is positive, a nitrogen, this nitrogen is positive, so we're not protonating this nitrogen. Can he be a leaving group? No, because that's just not set up to be a leaving group right now. A leaving group leaves from an sp3 hybridized carbon only, and never from an sp2 hybridized carbon. So no, no. Is this going to be am I going to deprotonate this? No, because I see all of these positive charges. These are not basic conditions. So first step, this oxygen atom functions as a nucleophile. Be a nucleophile. All right. Okay, so the water molecule attack function is a nucleophile, and now a lot of fiddling and diddling with protons. So I'm going to deprotonate this oxygen. The first time that proton goes off into the solution, and we're going to bring it back on this nitrogen atom so that this nitrogen atom can function as a leaving group. It's almost ready to do that. It's on an sp3 hybridized carbon. But if I let this guy leave now, it's going to leave as N minus. And I have no indication that these are basic conditions. Okay, so that's going to be a proton hop, a protonation, deprotonation sequence. So deprotonate this. What did I do? Yeah, okay, deprotonate him and protonate over there. Okay, so protonate that nitrogen the first time, deprotonate this oxygen the first time. Okay, so now this thing can function as a leaving group. This nitrogen atom can function as a leaving group. Be a leaving group, check. And just to speed things along here, I'm going to represent that. I'm going to push that leaving group out with the electron pair on that nitrogen, on the oxygen. All right, and now this nitrogen atom here picks off this proton, and the oxygen gobbles up that electron pair. So I protonated that nitrogen the second time, and I also deprotonated this oxygen the second time, and so I accomplished all of my goals. So that would be the mechanism for this reaction. Okay, so let's finish up with some, I guess maybe we have time to do one synthesis problem. Okay, so let's try to synthesize this molecule. So there's a starting material, but the other compound you have to use is a stable 2-carbon compound. That means it's something that you could get at Chemicals R Us. That means not a carbocation, not a carbene, not some kind of crazy, unstable, high energy species. Something, that where every atom has an octet of valence electrons. It's not a carbocation, it's not a carbene, it's just a regular stable compound. So maybe you're thinking of what the key you're thinking of strategy, you're thinking of tactics. The strategy is what are the key what is the key reaction, or what are the key reactions? That's the strategy. The tactics are, well, can I just accomplish it in a linear fashion, or do I have to have do I have to prepare the way? So there are a couple of ways of doing this problem. One way would involve, as the key reaction in the strategy would involve what? Key reaction. a Grignard reaction, because the product of a Grignard reaction is an alcohol, where the alcoholic carbon used to be a carbonyl carbon. And the Grignard reagent brings in an organic group that wasn't there before. So I could make this molecule using a Grignard reaction. But another thing we have to worry about is that the Grignard reaction, we can't have any OH, NH, or SH anywhere because the Grignard reagent is a strong base, and we can't just attack this with a Grignard reagent because we can't have OH, NH, or SH anywhere. So the strategy is Grignard, but the tactics, protection. Okay, so what I would do first is let's make the Grignard reagent. So what would be the Grignard reagent that I would need here? I would begin with this stable 2-carbon compound, right? That's not a carbocation, it's not a carbene. Everything has an octet of valence electrons, everything is happy. And make the Grignard reagent by reaction with magnesium. And magnesium inserts itself between the organic group and the halide. So there's my Grignard reagent. Okay, but I can't react this guy with this guy until after I've protected him up. So meanwhile, back at the wrench, while my lab partner is making this Grignard reagent, I'm over here protecting up this ketone, getting rid of these OH groups, which are the offending OH groups. And how am I going to do that? How do you protect a 1,2-diol as an acetal? So I would react this with some kind of cheap and abundant aldehyde or ketone. Acetone is good enough. And that ties up those 2 OH groups as an acetal. What's an acetal? It has an sp3 hybridized carbon bonded to 2 oxygens, neither of which is an OH oxygen. Okay, hello, yes, question about something?
Yes, sorry, Professor, I had a question about, I thought earlier you said that a leaving group cannot leave from an sp2 hybridized carbon.
Correct.
Or is this a different thing that's going on right now with a...
Where do you see a leaving
that doesn't bromine leave first from the carbon to form...
Let's see, leaving group is you have a nucleophile and you have an sp3 hybridized carbon, and the nucleophile attacks that carbon and kicks out the leaving group, and that would be the mechanism. But maybe you remember that the mechanism for formation of the Grignard reagent, this magnesium doesn't come in here and kick out Br, right? The Br doesn't get kicked out, the Br's still here. Oh. Right, so this formation of the Grignard reagent does not involve a leaving. This is a radical mechanism. So does that help?
Yeah, definitely. Thank you.
Okay, so now I'm ready. This guy plus this guy. Get them together. I've solved my problem here. I don't have any OH anymore. So get this Grignard together with this guy here. And I have this intermediate. Okay, that's looking pretty good. And now, after I run a Grignard reaction, I always work up with aqueous acid. Another question about something?
Sorry, I accidentally didn't remove that raised hand. I'm sorry.
Oh, okay. All right, so after we do a Grignard reaction, we nearly always have workup with aqueous acid. So we're going to do that again. But H3O plus, that is also the way of deprotecting the diol. That's H3O plus hydrolyzes the acetal back to a carbonyl compound and two OH groups. So that acetal oxygen is going to fall off as an OH oxygen. That acetal oxygen is going to fall off as an OH oxygen. And the acid is also going to work up the reaction mixture. And so that brings our synthesis to a close.